So I think we've gone through the front page and then the brute force section at the very top. We haven't done anything with the rational root tests. But this is all of the tests that we'll have. And so the things that you haven't seen are in the new packet that we haven't gotten to yet. But just to kind of have everything all together. Okay, so we can kind of go through some of this information. I also included just like our definition of irreducible and reducible in terms of our integral domains. And then also if we're working with a field, we can talk about this in terms of degrees instead of in terms of units. And then also recognizing that if you have a polynomial where you can write it as k times something else, where k is an element inside your field, so it's a unit here. Really, we can think a lot of the information that I know about F, or I know about G, I know about the other one. So this is when we call them associates. We had talked about this briefly, but things like the zeros of one is going to be the zeros of the other. If one is reducible, then the other is reducible. One is irreducible, then the other is irreducible. So just to kind of keep that in mind. But we did have our irreducibility tests for degree 2 or 3. This is our nicest case when our coefficients come from a field and our polynomial either has degree 2 or 3. We looked through the proof, and really what we were able to say is if it was able to be factored, then you'd have to have a linear term show up. And if you have a linear term show up, then you're going to have a root inside of the field F. So this is telling us that F is going to be reducible if and only if we have zeros or roots inside of capital F. And so again, because this is if and only if, anything I know about F being reducible or irreducible is going to tell me information about if I have roots or if I don't have roots inside of my field F. So this is most helpful when we're working with a finite field. Our nicest finite fields are really the only ones that we've talked about are our ZPs, where P is a prime. And so you can actually test, does it have any roots? If it has a root, then I can factor out a linear term by writing x minus what that root is. If it has no zeros, then immediately I can now say that it's irreducible. But we want to be careful. It has to be degree 2 or 3, and the coefficients have to come from a field. Right, this was an integral domain that wasn't a field, like let's say Z6. This no longer works. Some like weird things can happen if I'm not working with the field as my coefficients here. Okay, so that's kind of our nicest one. Anytime we see degree 2 or 3, we want to think here if we're in the correct, like if we're in a finite field, that's going to be helpful. But we'll see our mod P irreducibility test is really allowing us to think in ZP instead of in Z. Okay, information about being reducible over Q tells us about if it's reducible over Z. So here, if I have a polynomial with coefficients in the integers, as soon as I know it's reducible over the rationals, then I know it's reducible over the integers. Right, and I can think contrapositive. If it's irreducible over Z, then it's going to be irreducible over Q. Some things to know is my coefficients have to come from my integers. And this does not mean if it's irreducible over Q, then it's irreducible over Z. And we actually saw an example where it was irreducible over Q, but the way that we wrote the factors gave us non-units in Z, and so it wasn't irreducible over Z. So this is not true in general. So I only get this one direction, and I can also think the contrapositive as well. Okay, the newest one that we learned was our mod P irreducibility test. Here we're going to say if we can find for a prime P and a polynomial with coefficients in the integers, so always our assumption is that the coefficients are from the integers, where the degree is greater than or equal to 1, so it's not a constant polynomial. We can think about reducing all of the coefficients mod P. So that our new polynomial f tilde lives inside of ZPX, so coefficients in ZP, which is why it's important that our coefficients first started with the integers and not rationals or real numbers, but integers in particular. Then what we find out is that information about reducing f in terms of its coefficients is going to give me information about what f does over the rationals here. So if I reduce all my coefficients and I find out that this new polynomial here is irreducible, which is easy for me to decide in ZP. If it's degree 2 or 3, I just plug in my values in here. Not necessarily easy if I have bigger degree, but it at least shrinks what I'm working with in terms of the coefficients. And if my degree does not shrink after reducing it, so really looking at the first coefficient, if it's not a multiple of p, then it's not going to shrink in its degree. And again, if my f tilde is irreducible over ZP, then my f is going to be irreducible over q. Okay, so again, note our coefficients come from the integers. We want that the degrees don't lower. If they do lower in degree, we can't apply the theorem. So that's something to look out for. And really, we need to hunt for a p. We need to hunt for a prime number so that when we reduce it, the degree doesn't move down, and so that we can say something about f tilde in ZP. So not every p is going to be able to be applied here, and not for every p am I going to be able to say that it's irreducible. So it won't be helpful in those cases. Some things to be careful about is this doesn't tell me if I know it's reducible here that it has to be reducible over Q. So we want to be really careful to not conclude something if I know it's reducible mod P. Okay, so that was the last major test that we looked at. The last thing that we kind of did was something through brute force, was deciding right here, really what we first started to do was we started to look for roots to see if we had linear terms showing up. And if I found a root, I can find a way to factor it, and I know it's going to be reducible. If I don't find a root, I can't necessarily conclude anything unless it's degree 2 or 3. So if I know that I don't have a root, all that really tells me is that I can't have a linear factor if I'm working under a field. If I'm working under an integral domain, things kind of go different. Or if I have zero divisors, things can go weird as well. But here, if I'm working with coefficients in my field, if I know I don't have a zero or a root of my polynomial, then I know I'm not going to have a linear term. Because if I have a linear factor, then I'm going to be able to find a zero that lives inside of my field there. Okay, so you can keep looking. If there are no roots, again, that's telling you have no linear terms. That's also telling you that any degree 2 or degree 3 factor has to be irreducible, because I can't factor those into linear terms as well, right? So really what you end up doing is finding all the possibilities for the factors, really in terms of their degree. So if I have something like degree 6 and I know I have no linear terms, my possibilities for degrees are 4 and 2 and 3 and 3, right? I can no longer do 5 and 1. And then within those categories, you decide what do they have to look like, and are any of them actually viable, right? And when I have things like degree 2 or degree 3, I know if I have no roots, then I can't factor out a linear term. And so those would have to be irreducible also. And so you decide which ones do I have, which polynomials do I have are irreducible, especially over ZP. It's much faster for us to decide because I have less options for my coefficients. And then once you've decided which ones of those are actually viable, you can use your division algorithm to decide, is it actually a factor or not, right? So you divide by the factor that you think it is. You look at the remainder. If the remainder does not equal 0, it's absolutely not a factor. If the remainder is 0, then it is going to give you a factor, and you use the Q, the quotient, and whatever you divide it by to tell you exactly how to factor it out, right? And maybe sometimes like within some of these steps, we use like a different method to help us conclude something or to help us take away some of the cases here. But really, we're looking at it like case by case and deciding which ones actually work here and for what reasons why some of them were not going to work. Okay, but that's the last one that we got to last time. And so we'll talk about some of these, like the rational root test, which you might have seen in your pre-calculus classes. And we'll go through kind of talking about when we can apply it, when it looks like we can't apply it, but we actually can. But we'll go through some of these other theorems in a little bit more detail in our packet here. Okay, so our last example that we did was one where we did it by brute force, right? So this is where I had a polynomial degree 5. Okay, and I wanted to use my mod P test, irreducibility test. And so I told you to consider the prime equal to 2. And so we reduce everything mod 2. So anything that had an even coefficient disappeared. And so now I can think of this new polynomial in Z2x. Okay, so if we can show that this is irreducible here, then I know that this polynomial is going to be irreducible over Q. If I can show this is reducible here, it's inconclusive. I can't say anything further. All right, so the goal really in this example was to show this was irreducible, to tell us that this was irreducible over the rational numbers. Okay, so here, right, we're now working in a finite field, which is why this mod P is actually super helpful, because there's less things that we need, that we can use for our coefficients. And if I have degree 2 or degree 3, I can actually check all the roots. So the first thing that we do is we check, do we have any roots to tell us that we have linear factors? And the goal is to say no on all of these because we want it to be irreducible. So we check if we plug in 0, if we plug in 1 into my f tilde, I don't get 0 back out. So it's telling me I don't have a root, and so I don't have a linear factor. And so if I can factor it using degree 2 or degree 3 polynomials, they have to be irreducible. Because if they were reducible, then I have a linear factor, but then it'd be a linear factor of the original polynomial as well. Okay, so here what we ended up doing is by brute force again, and really thinking about if I could factor this, what would the degrees look like for the factors? Here I have something degree 5, and I said none of them can be degree 1 because it can't be linear. So I can't have 1 and 4, so my only options are 2 and 3. And we picked the one with the smaller degrees. It's less work to do here. If I can show that none of these are factors, I'll have a lot more options for degree 3, because I'll have another coefficient to take care of there. Okay, so here, right, let's see. We looked at all of the degree 2 polynomials in Z2x that were irreducible. So first we just started looking at the ones that were degree 2, and then we decided, can I factor them? Do they have zeros? If I can do either, then they're not viable options. So here, because I'm working in Z2 also, it simplifies a lot what the leading coefficient has to be. My only options are 0 and 1. My leading coefficient can't be 0, so it has to be 1. So all of these have leading coefficient 1. And then the coefficient for my x and for my constant, or I have options of 0 and 1 here. So I really have 4 options in total. The first one we saw, if I plugged in 0, I would get a root. And really, I can think of it as x times x. Here, if I plug in 0 again, I get a root, and I can think x times x plus 1. On this last one here, if we plugged in positive 1, we'd also get 0. And we found a way to factor this as well. The only one that ended up being irreducible was our x squared plus x plus 1. And we can show it's irreducible by plugging in 0 and 1 and seeing that we don't get a 0 back out. So it's really nice when it's degree 2 or 3 when we're working with the field as our coefficients. So this is really telling us if I was able to rewrite my f tilde as g tilde h tilde, where this one is the degree 2 one, this is my only option. Right? I don't have any other options. And so now I check. If this is my only option, does it actually work? If it doesn't work, then it's going to be irreducible. If it works, then f tilde is reducible, and I can't say anything else. My theorem doesn't let me conclude anything if I show f tilde is reducible. Right, so we didn't actually show the work for this, but we do our division algorithm, and we find that our remainder is equal to 1. And so that immediately tells me that it can't be a factor. And so this can't be, right, this can't be a factor for f tilde. And this was my only option for my degree 2s. And so f tilde has to be irreducible. And so this now tells me that f has to be irreducible over q using my mod p theorem here. Right, so lots of steps in here, lots of different things to apply, doing our mod p, but even within that, having to show some more work through different cases to decide, is it actually going to be irreducible or not? Okay, something that we want to be careful about is, again, if we can show F tilde is reducible over ZP. It doesn't tell us anything about F being reducible over Q. Really, again, it's going to be inconclusive if I can show it's reducible. I can only conclude something if the degree doesn't change, and it's going to be irreducible over ZP. And so we're going to look at an example here where we actually show it's reducible, but then somehow it's going to be irreducible over Q here. Okay, so if we look at P equal to 2, right, we have to look at our primes and kind of decide what can we conclude here. So here for Z2, so I can think P equal to 2. My F tilde here, again, anytime I see an odd number for my coefficient, it'll turn into a 1. Anytime I see it even, it'll turn into a 0, so it'll just disappear. Here I'm gonna get an x cubed plus x squared. Right, my -3 can turn into a +1 here. I really want to think 0 and 1 because I want to do things in Z2 here. But technically, -1 or -3, these are all equivalent mod 2. Yep. Okay, and immediately here, I know I can write this using x squared and x plus 1, right? Anytime you don't have a constant term, you know, all of these are going to have an x in common. And so at bare minimum, you can pull one x out in the front. None of these are units in Z2. So really this is telling me that F tilde is reducible. Okay, but again, I can't conclude anything about F over my rationals. I would have to use another prime to be able to show that it's irreducible here. I mean, and possibly it's not irreducible. Possibly I can factor it in some form. But really here, the goal is to find a P where I can show that it's irreducible if I want to apply this theorem. Okay, and so if I choose a different prime, if I choose 5 instead, right, and notice I'm not going to use 3 because if I use 3, my degree is going to go down because my leading coefficient is a multiple of 3. Oh. Okay, and again, I'm going to think about what will my new polynomial look like if I reduce all my coefficients mod 5. And again, it's important that our original polynomial had integer coefficients, or else I can't do this reduction. Okay, when I do this, I'll get a 1x cubed. I'll get a positive 2x squared, positive 2x, and a positive 3. Okay, so here we notice the degree did not go down. And the nice thing about this one here is degree 3. So here, when I have degree 3 or degree 2, all I need to check is if I have a field for my coefficients, so I have any roots in my field here. If I have roots, then it's going to be reducible. If I have no roots, then it's going to be irreducible. So really the goal here is going to be able to show I don't have a root for one of these p's. So hopefully it will work for our 5 here. So again, this is degree 3. So we check for roots. And we're working in Z5. So we plug in 0. This is our easiest one, right? We always just get the constant back out. So I get 3, which is not equal to 0. So this is not a root. It turns out that if I plug in 1 or 2, I'll get 3 mod 5 back out. And this is the type of thing, right, we don't want to have to do by hand, doing all these powers and reducing them on 5. We want to feel comfortable using our calculators to do some of this reduction for us. So we want to make sure for our quizzes and our exam that we have our calculators ready and that we know how to do the reduction mod a number. If we don't feel comfortable with it, feel free to come to me during office hours and we can look. It's pretty easy with the TI-84 to be able to do that. Okay, and then the last one here, f of 3 when I do 3, and the last one I needed to check was f of 4, which again did not give me back 0. and I checked all of my numbers 0 up to 4, none of them gave me back a root. And so F tilde is irreducible. And so by my mod P theorem, I know that F is going to be irreducible over Q. So even though when I checked for 2, I found that F tilde was reducible and my degree didn't change, again, I can't conclude anything with that information. I can only conclude something if it's irreducible mod P. If it's irreducible mod P, then I know it's going to be irreducible over Q instead. So F tilde irreducible over Z5. And so the original F is irreducible over the rationals. And a lot of our information is going to end up being, is it irreducible over the rationals? Because most of our tests are going to be specific to the rationals here. Yeah.
So if every single P that we tried is full, then we couldn't.
Yes, the only issue is that the prime is, we have an infinite number of primes. So even if I checked 30 primes and none of them worked, it doesn't mean that I couldn't find another prime that would work. In our case, I probably wouldn't make you check past like 7 or 11. Really, after that point, you can assume that that test is not going to work and you're going to have to do something else for it, either to show it's reducible or to show it's irreducible. Yeah. But if there was some way for us to say, no matter which prime you chose, you're never going to get a root mod P, then that would be enough. Actually, I guess. Right, maybe that would make you want to think that it's going to be reducible and you'd want to decide, am I going to be able to factor it in some other way? But I don't think we can directly say if there's no P that we can assume that it's reducible here. Okay, let's look at this next example where we'll notice that our coefficients are in the rationals. So I don't have integers working here. And so lots of my theorems depend on my coefficients being from the integers and then concluding something over the rationals. And so what I want to do instead of thinking of this polynomial is I want to think of a polynomial that's really closely related to it, that will give me the full information about F, but where I have integer coefficients instead of rational coefficients. That way I can use my test to tell me something about that new polynomial that I was working with here. Okay, so again, none of our theorems work, or we can't apply any of them here because this is not in ZX. Okay. But again, we're going to consider a new polynomial associated to F, where they really hold the same information. I say associated to F because I really mean I want them to be associates. I want it to be a constant multiple of the other. So I really want to take something in the integers and multiply it by F. I really am going to have the same information between F and my new function, my new polynomial here. But the goal is really, we can think, I want to get rid of the denominators, right? I want to somehow not have denominators on any of these here. So I just have integers showing up. So what could we possibly multiply to F so that we could get rid of the denominators, to clear the denominators? 35, right. If I picked 7, it would clear these two. It almost clear that one. If I picked 5, it only clear the last one. And really, I can look at my denominators here and take my LCM between them, right? My least common multiple is going to work here. If I don't want to calculate the LCM, I can just multiply all the numbers together, and that will definitely work. It just might give me really big coefficients to work with there, right? So I'm going to take 35, the LCM of my denominators, and I'm going to multiply that by F. Okay, and when I do this, what do I get back out? 15x to the 4th. Minus which constant? Yep, 10x squared. And we'll have plus 9x plus 21. Okay, and now what we've done is we transform this polynomial. So we technically do have a new polynomial here, but now all my coefficients are integers. And so now I can apply all my theorems that I have about integer coefficients to this new polynomial here. And really, if I can reduce h, I can even think here, because I'm working in a field, I can put a 1/3 being multiplied on both sides. And so if I can factor h, I have to be able to factor f. And if I can't factor h, then I can't factor f. So all the information about f is really held in the multiples of f. As long as I'm not multiplying by 0 here, then I lose all the information there. I really want to think the units here, because then I can move these around, and then I have information about both of my polynomials here. Okay, so factoring h will help us factor f. And vice versa, if I know it's irreducible, then I know f is going to be irreducible. Okay, again, this is why we call them associates, because they really hold all the same information that we care about, even in terms of the zeros. All the zeros are going to be the same here as well. Okay, so here, now that I have a polynomial with integer coefficients, I can use one of my theorems here to be able to conclude something. The first thing that we'll notice is that this is not degree 2 or 3. So showing I don't have roots somewhere is not going to help me to show that it's irreducible here. So the first thing that we can do is, again, our mod p. We can think, if I reduce these mod a specific prime and my degree does not go down, but somehow I can show that it is irreducible mod that specific prime, then I'm going to be able to show it's irreducible over the rational numbers, which is what I started with here. But again, because it's degree 4, it's going to take some work for us to show that it's irreducible, even if I have a smaller set of elements that I can work with here. Okay, so some things to avoid are going to be the primes 3 and 5, because then my degree is going to go down here. So let's try 2. And again, we want to avoid shrinking the degree, so we're going to avoid the primes that show up in the factorization of our leading coefficient here. Okay, so here I'm going to think, what happens when I reduce all these things mod 2? Again, I just need to think even and odd. So you have x to the 4th plus x plus 1. Okay, it doesn't hurt for us to check for zeros, right? Because if I do have a root here, then I know I'm going to be able to factor a linear term. But if I don't find a root, I'm not going to be able to conclude anything here because it's degree 4. Because it's not degree 2 or 3. Not having roots doesn't really tell me anything, because I could possibly break it up into degree 2 and 2. And those don't need to have roots. They both can be irreducible themselves. Okay, so here, again, it doesn't hurt to check, right? If this was reducible, this was going to help me. But also, because I'm doing this for h tilde to tell me things about h, the goal would be to find that it's irreducible for some prime, right? If I show it's reducible for a prime, it doesn't tell me anything about the original polynomial. Okay, but I'm going to check right here. If I plug in 0, I'll get back 1. If I plug in 1, I'll also get 1 back out. So this is telling me that I have no linear factors. If I have factors, like, it can't be linear. And here I'm working with degree 4. And so I want to think, what are the possibilities for my degrees? I could have had 1 and 3, but I know I can't have any of degree 1. So my only other option is going to be degree 2 and 2. So really, I want to think quadratic factors. And on top of that, because I'm not going to have any roots with the original, these quadratics have to be irreducible as well. So still need to check. Quadratic or degree 2 factors in Z2X. Okay, and this is actually what we studied last time. We looked at degree 2 and degree 3, actually only degree 2 irreducible polynomials in Z2 in particular. So we can just use the work that we did last time, or we can go through all of our degree 2 ones again and decide which ones are reducible or irreducible. But since we already did that work, right, that's what we did up here. In Z2, the only degree 2 that we had was our x squared plus x plus 1. Okay. So from our previous example. Okay. And now what can I do to be able to show that this is not a factor? Right. This is my only option. My goal is to show it's not a factor, because if it is a factor, then my h tilde is reducible, and then I can't say anything about h. So how do I check if this specific polynomial is a factor of my h tilde here? Right, and how do I conclude something using my division algorithm? Yep, whatever my remainder is completely determines if what I divided by was a factor or not, right? If my remainder was 0, that means I can write it as that factor times q. If my remainder is non-zero, I have to add it by something, and so it's not going to give me a factor back out. Okay, so here I'm going to use my division algorithm and study the remainder to decide if it's a factor or not. Okay, and you guys can check this work. Here, and again, we want to remember that we're working mod 2. So any of the work that we're doing for the coefficients, we really want to think coefficients 0 or 1, and always do that reduction. So at the very end, if you have things like in your remainder that have all even coefficients, that's actually your 0 polynomial. So it's actually the correct thing if it's a factor. But if you have any odd coefficients showing up, if you didn't reduce, that immediately tells you that your remainder is not 0. And so whatever you were working with was not a factor. But when we do this, what we end up getting is a quotient of x squared minus x and a remainder of 1. Oh, and I think this should be a minus 1. Although in this case, they're the same thing because we're thinking mod 2. Okay, so again, because my remainder is not equal to 0, I know that this guy here is not a factor. Because that was my only option for my degree 2s. And I already know I can't have any degree 1 with 4. Degree 2 and 3 are my only other options, but I have no degree 2s that are going to work. This is immediately telling me that h tilde is irreducible. And so h was irreducible. And so its associate f is also going to be irreducible here. So h tilde is irreducible mod p, so in Z2, which tells us that h is irreducible over the rationals. And so all of its associates, including f, which is the one that we started with, is irreducible over the rationals as well. So again, even though I started with a polynomial with rational coefficients, I'm always able to transform it into an associate where it lives in where it has coefficients in the integers instead, and then I can apply all my theorems on that instead. So even though I don't have direct theorems at the moment about rational polynomials, or polynomials with rational coefficients, I can always transform it so that it's instead about my integer coefficients, and then use that information to tell me about its associate, which has all the same information. Okay, questions on this one? Okay, so we're gonna look at our next packet. Again, just some more tests. And in particular, we have a bunch of tests for our rational numbers. What we're gonna see next is actually ways to check for roots. If I have a rational root, I know exactly what it has to look like. If I have a polynomial with integer coefficients, I can immediately tell you if I have a rational root, what it'll look like. It doesn't necessarily tell me I have to have a rational root. And the list is actually going to end up being pretty large of the things we need to check, but much smaller than all the roots inside the rationals themselves, right? Because previously what we saw was if we're working with a finite field, if I had degree 2 or 3, I can plug in all of my zeros to the side. This is kind of like the analogous one for my rationals. What things can I check for my roots in particular? Okay, and I don't believe that this one is included in Galleon, but it's a good check for us to find zeros, especially once we get past degree 3. It's really hard for us to find roots for them. But if I find a root, it'll help me to factor. So some of my goals are to decide if a polynomial is irreducible or reducible. If it's irreducible, I want to feel comfortable being able to prove that, which can be difficult. I'd have to use a bunch of my theorems to do this. If I can conclude it's reducible, being able to factor it until I have only irreducible factors showing up would be the next goal there. So this would be one step towards that because it helps me to factor out some of my pieces here. Okay, so here again, if I take a polynomial with integer coefficients, where, oh, and I didn't write it out. Actually, it's so fun. Okay, so here, if I have a rational number that's not equal to 0, so my R is not equal to 0, and I have it in reduced form, a fancy way to say that is that it has no primes in common, so the GCD of my numerator and denominator is equal to 1. If this rational number is a root of this polynomial, then I know exactly what it has to look like or what type it has to be. My numerator is going to depend on the constant term of my polynomial, and my denominator is going to depend on the leading both of these are coefficients, so this one's leading coefficient, and this is my constant coefficient here. So if I think R over S, I can think constant over my leading, and I really want to think what things divide it. So I really can think all the prime factorizations or all the divisors of it, then take the division of all those numbers that I found, and those are the possibilities for my rational roots. This doesn't tell me I have to have a rational root, but it says if I have one, it has to be of this very specific form. So here with this theorem, we're always going to be able to find all the rational roots. And even we saw before, if this was in terms of rational coefficients, I can always manipulate it until it looks like an integer polynomial and see if I could say any information about the roots of its associate and the roots of this polynomial instead. Right, if I have degree 2 or 3, now this is able to tell me if I'm irreducible now, right? Previously, I needed to work with finite fields because I wanted to check all the roots. But here I'm now downsizing the set of roots I could have. I now have this finite set within the rationals of what the roots can be. If none of them are roots, and I have degree 2 or 3, immediately I know it's irreducible now. Right, and we said, even though it requires it to have integer coefficients, we actually still can apply it to our polynomials that have rational coefficients, just like what we saw in our last example. Okay, so if we consider the following, where I have rational coefficients. So I have rational numbers showing up here. Okay, our rational root test, or RRT, doesn't directly apply, but we can, again, manipulate it until it looks like something that we can apply it. Okay, so here we can multiply our function, our polynomial. And here, what do we want to multiply it by? Yeah, I want to, again, get rid of or clear out my denominators. So I look at what my denominators are. I take their LCM to give me the smallest thing that'll work. I can multiply by 6 and 2. But some nice things that we have is when our leading coefficient, I guess here it's not going to work. When our leading coefficient is 1, when it's monic, it's a lot easier for me to decide what the factors might have to look like or what the leading coefficients of the factors look like. So lots of times we want to pick the smallest number, although regardless of what I choose, this is going to change the leading coefficient from 1 to 6. So here we're going to multiply it by 6. And we saw that this was the LCM of 2 and 6. And this is not going to change the roots, right? This is going to have the same exact roots as the roots of f. So all the information I find about the roots of 6 times f is going to be exactly the roots that I have for f. Okay, but we can multiply by 6 and we won't change the roots. And multiplying by the 6, we call clearing the denominator. Okay, so now I have 6 times f of x. So it's going to give me 6x cubed plus 3x plus 1. And now I have a polynomial with integer coefficients. And so now I can apply my rational root test to find the rational roots inside for my polynomial here. And again, because it's degree 3, so it goes degree 2 or 3, if I can show it has no roots in my field, immediately I know it has to be irreducible, right? Because if I could factor it, a linear factor would show up. And whenever I have a linear factor where my coefficients come from the field, then I have to have a root from my field. Okay, so if we have a polynomial with rational coefficients instead, there's always going to be some polynomial in Zx, an associate of f, which shares roots. Okay, so again, in a lot of these, we want to be able to say things about polynomials with integer coefficients, but we can always manipulate it by clearing out the denominator so that it ends up doing that instead. If I had something with the real coefficients, like things like square root of 2 showing up, I'm no longer going to be able to do that because I'm never going to be able to multiply by some integer to give you back all integers back out. So really this nice relationship between the integers and rationals doesn't work for every single integral domain and field that I'm working with. Okay. So what we're going to do is we're going to show that this polynomial here, luckily degree 3, is going to be irreducible over Q. Right, and again, because it's degree 2 or 3, if I can show I have no roots in Q, immediately that tells me that it's irreducible. Previous to this theorem, this would be really hard to do, right? If I put something generic like R over S for my x's, it would be really hard for me to show that that's never going to equal 0. Unlike if I worked with Z5, where I literally could write 0, 1, 2, 3, and 4, plug them in, and show I don't get zeros. With my infinite fields, it's much harder to do that. And so this makes it a lot easier for me to show if it has no roots inside the rationals. So this is most helpful when I'm working with degree 2 or 3 to show it's irreducible. But it also is helpful to find factors if I can find a root that comes from the rationals as well. Okay, so again, since this is degree 3, G is irreducible if and only if G has a root in the rationals. And it was important that this was a field. But if it wasn't a field, then I couldn't apply that theorem. Like if I had the integers or Z6, things like that, things work out a little bit differently. Okay, what we notice also, I have integer coefficients. So I don't have to do any clearing of my denominators. But if it wasn't integer coefficients, I would clear my denominators and turn it into the something that had integer coefficients instead. So we can apply a rational root test. So what we want to do is decide what is our leading coefficient, what is our constant coefficient, and then decide if I have a rational zero, what would it have to look like? And I take the factors of my constant and I divide it by the factors of my leading coefficient, right? That's what this piece is saying. My numerator depends on the constant, and my denominator is going to depend on my leading coefficient. So this is going to be another place where it's really nice to have a monic polynomial. If I have a leading coefficient of 1, I can really make this part disappear, and I just look at the factors of my constant, and it reduces the things that I have to check. Okay, so here we want to check what is our constant term, and then look at its zeros, and then look at its factors, because I want to think whatever that number is, I want it to divide what my numerator is. So here, what is my constant term? Here, this is equal to -1. And what about my leading coefficient? Right, and here, this is degree 3, so I'd write this as a sub 3 is also equal to 1. So I really want to think what integers do this -1 divide, which integers, and what does 1 divide here? So what would be my options for my numerator and my denominator? Both of them could be plus or minus 1. Lots of times we forget about the negative values, but it could be positive or negative. So can always think about the factorization of these numbers and then do plus or minus, right? If I had something like 10, I'd have plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. So look at all the factors, and you do want to include 1 in the number itself. Okay, so here the possibilities for my numerator are is going to be plus or minus 1. For my denominator, it's going to be plus or minus 1 as well. And I want to take all my choices here and divide. I'm going to take all my numerators, divide them by my denominators. This one's really simple. I'll just get plus or minus 1 every single time, right? I can think positive 1 over plus or minus 1, and then negative 1 over plus or minus 1. So here, R over S, the possibilities here are just plus or minus 1. Okay. In terms of the signs, we don't have to be that careful. We can just think, if I just look at 1 and 1, what are my possibilities for numerator and denominator? And then in my final answer, I can put a plus or minus. So you don't have to see matching up all these two with these two. I just think 1 and 1 and put plus or minus in the front. Okay, so these are the ones that I'm going to plug into my G polynomial. And I'm going to decide, do I get a root? If I get a root, I know exactly how to factor it. I'll take x minus the root, use my division algorithm to tell me exactly how to factor it. If neither one of these two gives me back a root, then I know it has to be irreducible because this was degree 3. If it was degree 4, I wouldn't be able to conclude that. I would have to use some other test to help me to do that instead. But what we do notice, right, is looking at the factors of these two, instead of looking at all of my rational numbers, I only have to look at 2 rational numbers, and they'll completely determine if I have a root or if I don't have a root inside the rationals. So here I'll plug in 1. And when we do this, we'll get back 5. Is that right? Yep, you'll get 1 plus 4 plus 1 minus 1, which is not 0. So positive 1 is not a root. If I plug in negative 1, I'll get minus 1 plus 4, minus 1 minus 1, which should give you back 1. And again, this is not giving back a root. So this is saying no rational roots. And again, because this is degree 2 or 3, and because my rationals are a field, this immediately tells me that this is irreducible. I can't factor this. Okay, so this helps us in multiple ways. This can help us to show something is irreducible over Q, but it also helps us to find roots if I have any rational ones. It doesn't necessarily tell me I have to have rational ones. I could have things like irrational solutions or complex solutions. But if I know for sure I have a rational one, I know it has to be of this specific form now. Okay, let's look at our next example. And here we're going to get a lot more possibilities because the factors of 12 are much more than the factors of 1. Okay, so what we want to do here, actually, we're not going to show it's irreducible, it's actually reducible. What we want to do is we want to factor it into pieces of irreducible polynomials. So I want to be able to write them as products where all the polynomials showing up I know are irreducible, right? So the first thing I could try to do is find a 0, and then I know I can factor out x minus that 0. Okay, so again, we're going to look at the factors of our constant polynomial. This is going to give me the information of my numerator. So here my options are plus or minus 1, plus or minus 2, 3, 4, 6, and 12. Okay. If I look at my leading coefficient, my A4, that's equal to 2. So the possibilities here are going to be plus or minus 1 or 2. So I want to decide what are the possible roots, the possible rational roots here by taking the factors of my constant and dividing it by the leading coefficient. And again, this isn't telling me that all of these are roots or that any of these are roots, but if I have a rational root, it has to be one of these that we'll write out here. Okay, so having plus or minus 1 as my denominator is the easiest one. I just list all of these out, because any of these divided by plus or minus 1, it's going to be plus or minus that number. So I'll have plus or minus 1, 2, 3, 4, 6, and 12. And now I want to think divide by 2 and then do plus or minus. And I'm not going to write repeats, right? It's already going to be a pretty long list. I don't want to have repeats in here and double check something I had already checked. So anything that's even, right? This will give me back 1, 2, and 1, 2, 3, and 6 already is in my list. So I'm going to look at the ones that are not even. I'll get 1/2, 3/2, and that's it. Right, this is the same as 1.5. You can write them as decimals or write them as fractions as you'd like. Okay, so it did reduce the roots that we would have to check here, but this is still a pretty long list. Right, how many do we have? 1, 2, 3, 6, 7, 8, 16 roots. The good thing is that we do have our calculators to help us with some of this. But some things that I might do is just ask you for the possible roots and then tell you, use this one as a root or check that it's a root and then use that factorization, because I don't want you to spend all this time plugging in all of these roots here. I guess something that we can know, this is degree 4. So at most, I'm going to have 4 roots showing up here. So if I found 4, I don't necessarily know they're all going to be rational numbers. But if I found 4, I can stop. It would be pretty lucky that the first 4 that you picked were the ones, or that all of them were going to be rational. But that at least tells you if you did find 4, you can stop at that point. So I say all we have to do as if it's not a big task, but it's a much smaller task than checking all the rational numbers we wouldn't be able to do. So Again, all we would have to do is plug in the candidates for the roots to see which give us back roots. So where will I get 0 when I plug it into F? If there are any, right? Just because I have a polynomial with integer or rational coefficients does not mean that all of my roots have to come from the rationals or from the integers. What we'll talk about later is that there is actually a biggest set that we have to go to. Something that we'll notice, right? Something like x squared plus 1. I know I need my imaginary numbers. So at the very least, I need my complex numbers to be able to answer all of these problems that might have real coefficients or rational coefficients showing up here. Okay, so what we're gonna do is, I'm gonna give this again for you for free. If we plug in -3 in here, we should get back 0. Almost always, I check plus or minus 1 because those are the easiest ones for me to see, especially the positive one. I just add up my coefficients and I decide, does that give me back 0? When I plug in -1, I have to switch the sign on the odd degree ones, and that will tell me if I get 0 back out. Just like if I plug in 0, I just look at the constant terms. It's a little bit easier for us to do this instead of actually plugging everything in and adding and then reducing it there. But in this specific case, it does turn out that -3 gives us back 0. And so what we would want is to be able to write this as x minus -3 as a factor. So I need to use my long division here, right? And the more and more that we do these, long division is going to feel like a long process to do here. So we can actually, we'll go through an example of doing synthetic division instead, which only works if you're dividing by a linear factor. In particular, it's nicest when it's x minus or x plus a number where the leading coefficient is 1. So we'll use our synthetic division. It's really essentially the same work, but written a lot quicker. You're kind of doing everything all at once here. So we're going to use synthetic division. But again, in general, I can't use this method if I'm not dividing by a linear term. If I'm dividing by something quadratic or bigger, synthetic division doesn't actually work. That looks like x plus b or x minus a number. Information that we need first is we need one of our roots so that we can do this synthetic division here. Okay, so what this is telling me is that x minus -3 or x plus 3 is going to be a factor. And so I want to take my f and I want to divide it by x plus 3, see what do I get back out, then take that new polynomial and try to factor it again or decide it's irreducible there, right? The goal is to be able to write out f using factors that are just irreducible polynomials. Right, so x plus 3 is a factor. And immediately we can say f is reducible. So we can always say if you have a root, then it's reducible over wherever the root lives. But if it's has no roots, I can't always conclude something about my polynomial here. Okay. Right, so we're going to use our synthetic division here. And so we're going to take our polynomial f. We're going to take our coefficients. And we do want to have placeholders anytime we don't have one of our terms showing up or when one of the coefficients is equal to 0. But it looks like here we're not missing any. So all I'm going to keep track of is my coefficients attached to all of these, and I'm going to put them in the same order. So I'm going to have +2, 1, -21, -14, and 12. So this is representing my f. Okay, and I want to think x equal to -3 is the zero of this linear factor here. So the information I'm going to use here is for x equal to -3. Oh, and we're just out of time. So this will be a good place that we'll pick up on Monday. Finishing up this synthetic division, unless you guys really want to see this all the way through. This is much faster than our division algorithm or our long division, but again, only works when we're using our linear terms. And in particular, it's nicest when we have x plus b, because I know exactly what my roots would be for that one instead. Already. But on Monday, we're going to try to wrap up our packet here, which it might be a little bit close. Right, we have like 4 pages left. So I might have to go a little bit into Wednesday's class, but I don't think we'll have to go into that far through. And then the rest of the week is just going to be a review for the final. And so hopefully by Wednesday, I'll have a review sheet ready for you guys to be able to practice there. And then we can talk about like the proofs and things like that that will show up on the final exam. But if we don't have any other questions, and I'll see you guys tomorrow.